This video is about Chapter 5, and in this video we'll talk about understanding and comparing distributions. By the end of this video, you should be able to find the 5-number summary for a set of quantitative data and graph a box plot. You should also be able to compare 2 or more distributions, and you should be able to know when and how to re-express data. First, the 5-number summary. The 5-number summary are 5 numbers that are a quick summary of quantitative data. Those numbers are the minimum, Q1, the median, Q3, and the maximum. So here is our data from the previous chapter's video, and from this I can write down the 5-number summary as the minimum, which is 1.4, Q1, which is 2.2, the median, which is 3.1, Q3, which is 3.5, and the maximum, which is 4.0. This is the 5-number summary. Okay. Now it breaks up the data into quarters. So a fourth of the data is here, and a fourth of the data is in between these values. A fourth is in between these values, and a fourth is in between these values. Okay. And it gives us an idea of the center, the spread, because you can quickly find the IQR, and also the shape based on how the numbers are situated compared to each other. Okay. Now, it's kind of hard to see the actual shape of the distribution using a 5-number summary. And so we have found a way to visualize the 5-number summary by drawing a box plot. A box plot is a way to visually display the 5-number summary, specifically to look at the shape of that distribution. The place that you start when drawing a box plot is with Q1, the median, and Q3. Q1 is 1.15, so I draw a vertical line at about 1.15. The median is 1.9, and so I draw a vertical line at about 1.9. And Q3 is 2.93, so I draw a vertical line at about 2.93 and I connect them. So here is the box for our box plot. Now we have some things that stick out on the sides, which are often called whiskers. And so the minimum is at 0.2, and it sticks out like that. Okay, now the maximum is 8.67, which seems really far away. It seems like an outlier. Okay, so we have a rule of thumb when determining if something is an outlier or not. At least we do for box plots. So here is the rule of thumb for outliers. A data value that is less than 1.5 times the IQR below Q1 or more than 1.5 times the IQR above Q3 might be an outlier. Okay, that's our mathematical rule of thumb. We still need to look at the data value and see if it is different or not. Okay, but that's our rule of thumb. Our rule of thumb for something called far outliers are when it's less than 3 times the IQR below Q1 or more than 3 times the IQR above Q3. Those are for far outliers. Okay, let's go back to our box plot. Let's first find the IQR. The IQR is 2.93 minus 1.15, which is 1.78 is the IQR. So the lower fence is going to be Q1 minus 1.5 times the IQR, which is negative 1.52. And the upper is 2.93 plus 1.5 times 1.78, and I get 5.6. Okay, so our fence, our lower fence, let me choose a different color. The lower fence is at negative 1.52. Okay, so the minimum value is within that fence and would not be considered an outlier. It doesn't seem different in the data. The upper fence is 5.6. Okay, so somewhere around here. Okay, and this maximum value over here at 8.97 does feel different to us. It's beyond that fence. Okay, now what I would pick is the data value just below this, somewhere in this area. Whatever data value is below that fence is where I would draw that line, and it would look something like this. I don't know exactly where this line should go because I pulled this data from the textbook and I don't have the actual data to use. So let's look at that. Here is the histogram and here is the box plot. Okay, now it looks kind of like the one we drew. The fence we found up here was 5.6, and the fence looks to be that the upper line looks to be right about at 5.6. Okay, now notice that there are some dots here. These dots are the outliers. Okay, the data values that are above the fence. Okay, and there's a star symbol here for the maximum. Okay, this is a far outlier. Okay, so sometimes we use a different symbol for far outliers than we do for other outliers. So let's talk more about outliers. What should we do with outliers? First of all, we should look at them more closely and try to understand how they are different from the rest of the data. Is something else happening? Is it some kind of a subgroup in our data that we didn't really notice was there? Okay, if the outliers are fundamentally different for some reason, it can be removed from your data set. Don't be too quick to do that, but if it's very different for some reason, then feel free to remove it from your data set. Okay? It also could be a mistake. You could actually have put the number in wrong as you're displaying the data or as you're typing it in, or the person who is responding to a survey may have made a mistake when writing the number down. There could have been some mistake, and if so, it can be removed from your data set. Okay, but if the data is valid, you should leave it in your data set. Okay, it presents a interesting case in your data. Okay, here's a quick review from last chapter. When you describe a distribution, you talk about shape, center, spread, and unusual features. When you compare two distributions, you should use shape, center, spread, and unusual features. You compare with the same types of things that you use to describe a distribution. So here's an example. We've taken the wind speed data and broken it between spring, summer versus fall, winter. And we compare the shape, center, spread, and unusual features for these two distributions. So first, the shape. I would say that the spring-summer distribution is more skewed to the right. And the fall-winter looks a little more symmetric, although it is slightly skewed to the right. Okay? The center, we can find looking at either the median or the IQR, that the fall-winter distribution has a higher center than the spring-summer distribution. Okay? When looking at the spread, we can also see that the fall-winter distribution has a higher spread than the spring-summer distribution. Okay? And the only unusual feature we want to point out is that there is an outlier for the fall-winter distribution. So I just compared the shape, center, spread, and unusual features for these two distributions. Okay, when you are comparing many distributions, you usually have to use box plots. There's just too much data, and so you summarize each set of data with a box plot, and then you can easily talk about how the centers are changing, how the spreads are changing, and other things about the different data sets using box plots. They're very handy when comparing multiple sets of data. Okay, re-expressing data. There are two goals, actually there are more, but we're looking at just these two goals of re-expressing data. The first is to make a skewed distribution more symmetric. And the second is to make several distributions have similar spreads. The way that we do this is often using logarithms and square roots. Here is one example where we used re-expressing data. This data comes from yearly salaries of CEOs, which is a very, very skewed distribution. Okay, so one of our goals is to make a skewed distribution more symmetric. Okay, and the thing we did with this is we took the log of their annual compensation and it created a graph that is much more symmetric and much easier to analyze and to look at than the previous skewed distribution. The second example is about the amount of the cotinine levels for three different subgroups who had different kinds of smoke exposure. Okay, and one of our goals of re-expressing data is to make several distributions have similar spreads. Okay, and that is what happened. It was much easier than to compare the different subgroups when looking at the re-expressed data than the original data. So this video was about understanding and comparing distributions. You should know how to find the 5-number summary for a set of quantitative data and be able to graph or sketch a box plot. You should also know how to compare two or more distributions using shape, center, spread, and unusual features. And you should also be able to know when and how to re-express data. Thank you for watching.